So, welcome to my presentation of today. Simulation of the dynamic interaction between pantograph and overhead contact line according to EN5318 using OpenRadioss. Really long title. You will get to know about it later on, what's going on. First of all, again, a few slides about me. One slide about me. As I already mentioned, I am a structural engineer at PGM. And my expertise is already in car body design and bogie design. First of all, I would like to talk a little bit about PGM, what we are, what we do. Then I would like to introduce you into the topic of today. I will talk a little bit about the standard of EN5318. I will talk about boundary condition and loads. At the end, some simulation results, and at the very end, some outlook of what we want to do. First of all, PGM. What are we? We are basically an overall group which is working in the field of railway systems. So we like trains, we deal with trains. That's what we do. We have PGMS Technik, basically a measuring company. We are accredited testing facility for engineering. We also have PGM monitoring, where we do monitoring, tracking, sensor system, and automation. We have PGM motion, where we do international project management and asset management, and we have the Railway Competence Center, RCC. We work worldwide in over 30 countries and over 60 continents. We have many years of international project management, and our company is around 80 people. When we talk about trains, we have to know that it's a regulated field. So you have many steps until you get a commercial operation of your trains. We start with a project idea. There we are mostly 3 of our companies are dealing with, and at the end we have a commercial operation. That means we can go on track with our trains or with customer trains or whatever. We work in all of these fields from the perfect. And the company I actually work for is the PGMS Technik. We, as I said already, we are an accredited test institute for railway vehicles. We are accredited for the following fields: vehicle dynamics, driving comfort, and instrumented wheel sets, fatigue strength, brake test, acoustics, aerodynamics, and pantograph and overhead contact lines. Furthermore, we do engineering, as already said, strength verification and multi-body simulation. Let's come to today's topics. It's the simulation of the dynamic interaction between pantograph and overhead contact line. To talk about this topic, we first of all have to know what an overhead contact line and what a pantograph is. Maybe if you ride a train or walk by train lines, you see these kind of structures. These are the wires where the electricity goes through. And here you also have the pantograph, which is basically taking the electricity from the wire to the vehicle. So you don't need batteries, you just ride with the electricity you get from up there. And we are interested in especially these points here. What is happening here? Usually you have a contact force there, yeah? But what is if you're driving 300 kilometers per hour? Everything is shaking. Do you have a contact loss there? If you have a contact loss, you might get electric arcs, and then you get wear or whatever. So this is what we are interested in. So why do we actually do this dynamic interaction simulation? We want to predict the current collection quality in advance. We want to support the approval process of overhead lines and pantograph designs. And we want to support vehicle manufacturers and infrastructure designers to optimize their designs by using simulation tools. As I said already, railway engineering is a regulated field, so there are always standards, and you have to follow these standards. The standard for the simulation for this kind of simulation is the European standard 5380. What does it say? It's written here. It tells us how we can validate the simulation of the dynamic interaction between pantograph and overhead contact line. Again, this long sentence, shortened, it just specifies how simulations must be structured, executed, and validated to ensure realistic and reliable results. How does it work? We have a two-stage process. First of all, we have to model a reference model, and we have to validate our simulation against that reference model. Second of all, in this standard, we can find real measurement data, and we also have to validate against these real measurement data. Only when we validated against both of these, against this reference model and real measurement data, we are allowed to do any simulation of contact between pantograph and overhead contact line in scope of this validated, within this validated scope. We are currently here. We are validating our simulation against the reference models. Let's talk about the reference model. How does it look like? The standard tells us there are 3 different reference models. The first one is here. You see, usually you have a carrier wire, which is hanging like this. You have some kind of droppers, and the droppers are connected to the contact wire. And the first simulation we have to carry out is using this kind of overhead contact line. It's called alternating current overhead contact line without wire suspension. You see, we have here a drag of 55 millimeters, so it's hanging a little bit through. It's not straight, yeah. To make it straight, there's an improvement where you use this so-called wire suspension. This is just an additional wire which you put in here to make the contact wire nearly straight. This would be the second simulation we have to run. Then, if you are also interested in direct current, you can also do DC overhead contact line. The standard also tells us we have to use at least 10 strands, so 10 times 55 meters, in order to simulate such problems. In reality, we have to use way more to get rid of transient effects or model boundary conditions. There are way more parameters than this. So as I said already, we have to model the span length or distance between the support points. That would be from here to here. We have to know where these droppers are positioned in our span field. We have to know the mass per unit length of each wire or cable. Also, these cables here, the carrier wire and the contact line, they are pre-tensioned. So we also have to model this. We of course need to know mechanical properties of the support and the structure. And we of course have displacement characteristics of the droppers. So these droppers here, of course, also force displacement dependent. Last but not least, we also have damping in our system. How does the model look like recreated in HyperMesh? First of all, look here. We are really talking about kilometers, not meters. So this is our range, what we have to simulate. How did we do this? What you see here is the initial condition. The initial condition is the condition without gravity applied and without any tension applied in the carrier wire or the contact line wire. Here you see the 55 meters, so this is one span. When I zoom in, I see exactly this. And I modeled it in a way that the carrier wire is straight and that the contact line wire basically has the inverse geometry of this here, what you see up here. after applying gravity, you will see that everything falls together, and we reach this static behavior of the standard. So what elements types did we use to model our model? For the carrier wire, or also for the messenger wire, we used beam elements. One element length is around 1 meter. So a little bit bigger than other models. And cross-sectional area of 120 square millimeters, and a pre-tension force of 16 kilonewtons. For the contact wire, we did some analysis, and we came up with an element edge of approximately 200 millimeters. The standard tells us you need to use a cross-sectional area of 150 square millimeters and a pre-tension force of 22 kilonewtons. Then, of course, we have everything has to be supported. So the messenger wire is supported here. It's just with a spring with some damping inside. Contact wire support in this model is here. Also just some stiffness. And we have the droppers, which you can see here. 9 droppers in total in one span. And we modeled them with spring 2 elements with defined stiffness. As I said, we also need some damping in our model, and the standard just tells us, okay, use some damping between 0.1% and 0.15% of the critical damping. Okay, the standard also tells us, okay, if you don't know what you have to do with that here, you can just use the Rayleigh damping, and you're allowed to use these coefficients. We did that. So we did implement the Rayleigh damping in our model. Then how does the model for the pantograph look like? The standard tells us, simplify it. Just use 3 masses, 3 dampers, 3 springs, and you're done. You see the units here, kilograms, so the mass 1, mass 2, mass 3 are around 10 kilograms. The damping varies a lot between all 3 of them, and also the stiffness varies a lot. Alternating current and direct current are different pantographs, of course. Yeah. How did we implement this in OpenRadioss or HyperMesh? First of all, we said, okay, we want to simulate a contact between the contact wire and the pantograph. So we use also beam 3 element here for mass number 3. That means this beam just gets a length, a stiffness across sections, and so we came up with the 7.5 kilograms for that one. Damper and springs are clear. It's just a spring 2 N element, and for M2 and M1 we just use mass points or solver masses, how they are called in radius, OpenRadioss. Okay, last but not least, which contact do we actually want to use in our model? As you can imagine, we have this bar here for our pantograph here, and the bar for our contact wire. So it's an edge-to-edge contact. I tried many contacts, but the only one working actually for edge-to-edge is type 11. It's a quite old contact type, I was told, but it's robust and complicated. But it has the same penalty formulation as type 7, so shouldn't be so bad. The standard just tells us you have to have realistic contact stiffness, maybe a friction force, and non-physical penetrations are not allowed. Okay, this is what we used. Then here you have some, I don't know if you can see it now inside the room here, but you have some contact adjustments, what you have to do. For example, you can say you want to adjust the maximum stiffness. You don't want that it has to, you don't want it to be larger than 1000 Newton per millimeters. You can also specify the minimum stiffness, or you can also specify the friction you're using in your contact model. What you see here are the adjustments for the best simulation results so far. So we are not done yet. Our model is not validated yet because we are not within the scope of the validation yet. But this is the best results, or this is the implementation for the best results so far. We will come back to the results later. What else do we have to know? We have to know how fast we go with our train. The first speed is 275 kilometers per hour. So high-speed train, yeah. There's a second train we have to simulate as well. This goes 320, so even faster. Yeah? And you can imagine everything shaking up there. You have a lot of vibration, a lot of movement, and also the wires are, you see some waves inside the wires, so there's wave propagation inside the wires as well. And not only that, you usually have more than one pantograph per train. So within this validation, we have to simulate 2 pantographs, and they have a distance of 200 meters between each other. The frequency range we have to have a look at is between 0 hertz and 20 hertz. And the standard tells us just that we have to use a sampling rate of 200 hertz. And we use at least 200 hertz, and we decided to go for 400 hertz. In the post-processing, we then have to use a 6th-order low-pass filter with a cutoff frequency of 20 hertz. That's for the dynamic simulation. If we have a look at the simulation results now, first result is the static load case. As I told you, you have gravity, which is acting, and then you pull both wires, one with 16 kilonewton, the other one with 22 kilonewtons. And you have to validate your static simulation against the values inside the standard. What do you have to compare? You have to compare the wire position at the droppers and cantilevers. You have to compare line elasticity at these points, and to compare dropper lengths. The standard gives you some tolerances which you're allowed to use. So if you stay with the contact wire position, you can have plus minus 5 millimeters. So if you apply gravity now, everything will sink down. Then we apply tension force in the contact wire and the carrier wire, and we get a shape like this. Maybe you remember the picture from the standard. Our carrier wire was formed like this. We have the same form now, the same geometric shape we have here. And the red wire, the contact wire, is nearly straight now. We see we have a vertical displacement or vertical position of 53 millimeters. The standard tells us, okay, you should have 55, but we are within the tolerances of plus minus 5 millimeters. That's good. This is for all other positions here as well. So static load case, good. We are within our tolerances. It's good. We can continue with dynamic simulation. What do we have to extract here? We have to extract the time history of the contact force, the standard deviation in time domain, standard deviation in frequency domain, maximum of the contact force, minimum of the contact force, vertical position range of the contact points, maximum vertical displacement at the support point, and the contact loss percentage. This is our result. We have 2 pantographs, as I said, and in order, maybe you don't see it here, there's 0, 20, 40 seconds. Yeah, so we simulated 200 seconds. The first 40 seconds were static load case, gravity plus free tension. I know it's a long time period for static simulation, but we didn't want to put any movement inside the wire because you have seen the damping is basically nothing. So we wanted to make sure that nothing is moving after static simulation. After that, we took the pantographs and put them towards to the contact wire. And this is the contact force you see here now. And we get around 200 newtons contact force. And then from second 45 to second 100, we accelerate our train from 0 to 275 kilometers per hour. this is what you can see here. You see it's highly dynamic, entirely nonlinear. What you see here, we have a lot of peaks in the contact force. And after 100 seconds, so when we reach our 275 kilometers per hour, we get with the rear pantograph in a periodic area. And this is a really nice result. It looks already really good. But the front pantograph, you see, we still have some peaks all around here. The reason for that is because the rear pantographs sends waves towards the front pantograph, and of course these waves are affecting already the front pantograph or the contact force of the front pantograph. And here we see some peaks. We have to get rid of them in future, but that's our future work. What's important now is that we have a look at the results. For the mean contact force, the standard says for the front pantograph, you have to have around 145 newtons. We have a mean contact force of 145 newtons. Perfect. For the rear pantograph, we should be around the same. We have 143. So we are within the scope of validation. But the maximum contact force, we are a little bit too high in both cases. But the front one is way higher than the back one. So way too high than the back one. Minimum contact force, we almost reach it in both cases. In the standard deviation, we are also not far away to reach it. In time domain, also in frequency domain, we are close to it, but we haven't reached it yet. The vertical positions of the contact point, we haven't evaluated it yet. This is a task for the future, but we also can say that we don't have any contact loss, which is already really good because this is not allowed. Yeah. Then let me come to the outlook, what we plan to do in future. Of course, we are going to fine-tune the contact settings for type 11 to achieve the required results for the reference model. Yeah. Then we want to reduce the simulation time. As I said, there's a lot of potential since we had 40 seconds for static load case and tensile strength and so on. We can reduce this a lot, I'm sure about that. And also, if you have a look at the results again, maybe if everything goes well, we just have to simulate until here because nothing is changing. So if we get for the first pantograph a similar result as for the second pantograph, then we can cut off already at 120 seconds, for example, and make the simulation faster. Then we, of course, want to simulate the other reference models. After that, we want to validate it against the real measurement data from line tests, like Appendix B of the standard. Then we want to compare the results from OpenRadioss to the results from our MATLAB model. Because since we are accredited, we're already simulating these kind of things, but with a different tool. And this tool is MATLAB, so we have our own MATLAB code for this. And after that, our goal is to go outside and measure the real tracks and the pantographs, and also implement real measurement data from ourselves. And for the pantograph, we built our own test rig already. This is what you can see here. I'm not allowed to show you better pictures, but this is what we have already. And with that, we want to evaluate these three masses we have seen before from the 1D mass spring damping system for several different pantographs. Last but not least, we also plan to do simulations including car bodies, the track itself, for example, journal passages, and we also want to include aerodynamic effects. We don't know yet how we will do it, but maybe some SPH inside it, we don't know yet. But with that, I'm coming to an end. And if you have any questions, don't hesitate to ask me, or you can also contact me if you want. I would like to thank you very much for your attention, and thank you.